Hello, I'm Allison Thorpe, and this is God Talk, recorded and produced in the bluegrass state of Kentucky, the home of horses, hills, hiking, hillbillies, big trucks, Wildcat basketball, and Daniel Boone, the state where guns are honored and shoes are optional. This is the show where science, faith, and culture are discussed openly.
Good afternoon and welcome to God Talk, a radio show where a rocket scientist and a medical doctor, who is also my pastor, talk about science and religion. I'm your host, Doug Thorpe, and with me as always is my co-host, Dr. Andy White. Today we have a special show on astrophysics on God Talk. And so, first of all, Dr. Andy, welcome to the show.
Thanks, Doug. I'm really excited about the chance to interview and discuss with an astrophysicist or a theoretical physicist the ideas that are so intimate and important when it comes to creation, to God, to our universe, and the relationship of science and faith. So this is God Talk, where we rightly divide the line between science and faith.
And this is God Talk, brain candy for the thinking Christian, a bad day for the atheist, and a provocative question for the seeker.
So, Doug, we're going to, in just a minute, interview Dr. Tom Pannuti, right?
Dr. Pannuti is a astrophysics professor at Morehead State University in the Space Science Center.
Okay, let's get him online, and we have a lot of good questions to ask him. So I hope we move things along and rightly divide the line today.
Okay, so hey, Tom, Dr. Pannuti, are you on the line?
Yes, I am. Thank you guys for having me on board.
All right.
Really happy to have you here, Dr. Pannuti, and we got a lot of questions for you today, so hopefully this will be more you talking about answers that Doug and I have been raising questions over the last several weeks, so we're real excited to have you. Thanks for being here.
So we don't usually do this, but we actually have notes today. We usually just talk off the cuff, and but we have notes. So if you hear papers in the background, this is where we try to ask informative questions. And how about start us off with telling us what is the Big Bang, what caused the Big Bang, and how do scientists know that there was a Big Bang? And I'm not talking about the TV show.
Sure. Yeah. Can you imagine if you told people years ago that the most popular sitcom on TV would be involve four physicists? They
I know. I know. Well, I am a self-proclaimed nerd. I'll just let you know. I am one.
Well, we
I
all
qualify.
are.
Yeah. So we do qualify for that club, but yeah.
Sure.
Yeah.
Sure. Okay. The Big Bang is what astronomers believe was the origin of the universe. Astronomers believe that it's always been debate about from scientists and philosophers about what the universe is, where it come from, did it have a start, did it have an end point. The currently accepted belief among astronomers that everything began from something called the Big Bang, which some astronomers disagree with this term, and that implies some kind of explosion of some type. But it's also seemed to wait for the general public. A misnomer about it is actually not understanding what it really is, in that it was an explosion of space and time, and everything kind of, for what we know and how we define space and time, it all began with this initial explosion, and there's been an outward motion since then. And what we believe, astronomers believe now, is that we figure that this event took place about 14 billion years ago. The way we can do that is we can actually, one line of evidence is what's called Hubble's law. Edwin Hubble was an astronomer who worked out in Pasadena, California in the 1920s and 1930s. He is a namesake for the Hubble Space Telescope, and he was also, I like telling my students this, he was the backup center on a national championship basketball team. When you work in Kentucky, this really resonates with the students.
Yeah.
So,
Okay.
Yeah. But what Hubble found was he looked at the spectra of galaxies, of galaxies, and he noticed a very remarkable trend. When we look at the spectra at the light of galaxies, we can actually, or any kind of astronomical source, we can know something about the motion of the object by looking for what we call either a red shift or a blue shift. We have the light coming from a source is a wave, and we're already familiar with, on a day-to-day basis, sound waves. If an ambulance is coming toward you or sound's coming toward you, the pitch is increased because you can imagine the sound waves are compressed, so the pitch is higher. If a light source is coming toward you, the light waves will be compressed to a shorter wavelength. We call this a blue shift. If an object is moving away from you, or sound is moving away from you, the pitch is lower, and the light waves are being stretched out. So this is what astronomers call a redshift. Hubble's big discovery was in a systematic survey of a large number of galaxies, he found that all these galaxies appeared to be moving away from us, such that you can actually find that the more distant the galaxy was, the faster the galaxy appeared to be moving away. And the big interpretation of this, first of all, this was a crucial yardstick for astronomers because, as I tell students, the toughest thing in astronomy is trying to figure out how far away objects are, trying to find out what their distances are. So with the Hubble's law, we can actually figure out how far away an object is if we measure how fast it's moving away from us, and there's a term called the Hubble constant. With the two of those, we can actually calculate the distance to a galaxy. So what Hubble found was the more distant galaxies were, the faster they're moving away from us. And this is often called the raisin bread analogy. If you imagine a loaf of raisin bread just starting to leaven, and what happens is all the raisins are moving apart from each other. And the thing to think about with this is that the galaxies are part of the space-time continuum. And as the universe expands, these galaxies are carried along for the ride. I try to describe it as kind of ships on the ocean in which these galaxies are. Because when we measure these redshifts of these galaxies, the way to think about it is when the light has left these galaxies on its way toward us, and it's taking millions of years to reach us, on its way toward us, the light waves, as space expands, the light waves are also going to expand too. They're going to be stretched out. And this light waves are going to have a longer wavelength when they reach us compared to when they've actually left. And the more distant a galaxy is, the more of a stretching that may occur of the wavelength to make the object appear to be redder.
Okay, let me break in there for a second. Now,
Sure.
What you described at the beginning sounded like the Doppler effect, that people can hear train whistles as the car is approaching and going by. It's higher pitch when it comes toward you, and lower pitch as it goes by. That's the Doppler effect, correct?
Really, the same thing. I wrote a book on radiographic imaging and on ultrasound. And it really sounds a lot like the same kind of technology where we were measuring vascular flow through a blood vessel with the Doppler effect. Yeah.
Yes. Thank you. This is better known as the Doppler effect, and it is absolutely indispensable to astronomers when we try to take the spectrum of trying to analyze properties of an object. One of the first things we try to do is to figure out its motion, and by looking at shifts in the positions of lines in the spectra of something, by looking by shifts towards shorter wavelengths or longer wavelengths, we can get a better sense of what we can understand what the motion of the object is. Hubble's breakthrough was to realize that the more distant the galaxy was, the faster the galaxy appeared to be moving away from us.
All right, I got to break in there. All right, you're saying that all the celestial objects in the sky are moving away from us. Is it us? Are we the problem, and everybody's trying to get away from us?
and the other question is, are we the center of the universe? Which
are we the center?
Like where's the center? Yeah.
Sure. Those are two very good questions. Right. We are not at any kind of preferred center. If you're in another galaxy and you tried the same experiment by looking at the motions of other galaxies, it would seem that everything is moving away from you. Mm-hmm. There is no preferred perspective, actually, from all galaxies. See them all moving apart from each other. Yes.
They're all relative to one another, then. It's a relativistic center. Okay.
Yes, and we can't say there really isn't a center of the universe. I joke with students that despite what they saw in Hitchhiker's Guide to the Galaxy, you cannot, go to a rocket ship and say, at this point, here's where the Big Bang took place. Because the Big Bang was an explosion, kind of took place everywhere at the same time. And so it's an expansion kind of everywhere. So there really is no center to speak of. We can say that there's a certain distance to which we can actually receive light from objects. Mm-hmm. We can say that the universe is 14 billion years old. We can say light has been traveling all this time and it's finally reaching us now. This is the edge of what we say the observable universe is to us. There's a distance there. But there is no center of the universe to speak of.
All right. Now the next thing is you mentioned Hubble and these observations, but you actually haven't mentioned the Big Bang itself, which I thought was discovered from a Jesuit priest who went to the Pope for blessing on his ideal.
Yes. Georges Lemaitre, and it's amazing to tell people that it was a Catholic priest and trained physicist who was actually the first person to propose the idea of a Big Bang. Often, sometimes they think it is a sterile scientist, but Lemaitre was an amazing person. He was actually, I was just doing some reading on him. He actually served in the Belgian military before he entered the seminary in World War One. He was very prescient with many things for the expansion of the universe. Also, the new concept of dark energy. He first proposed that. He was also one of the first scientists to really be very enthusiastic about computers, about using computers and high computing speed.
In the 30s and 40s, he's talking about computers.
This was more in the. He was actually. This was in the 50s and 60s.
Okay.
Yeah, I believe he passed away in the early 60s. But right when computers were kind of in their infancy in the 50s, he was a strong advocate. He was actually became something of a programmer himself.
Wow. So
yes.
No, that's interesting. I didn't want to cut in, but I was going to say from a historical standpoint, then we haven't really known about the Big Bang before the 1900s.
That's correct.
Okay.
Yes.
And was it Einstein against it? He thought it was a sterile universe.
Right, Einstein. Yeah, at the time there was two visions about what the universe could be. One was that the universe was static in the sense that the universe has existed as it appears and it does not undergo any changes over time. And the other opinion was maybe that the universe does go through some changes of some kind. Hubble's discovery that the galaxies were moving away from us, and the interpretation that means about the universe expanding, was almost completely by itself buried the steady state hypothesis of the universe, or the static.
And that's state. Accepted. That's pretty well accepted by most physicists today, correct?
Yes.
That we don't have an eternal steady state universe.
It is right. The astronomers and physicists believe in an expanding universe. There's a couple holdouts, but the consensus among astronomers is that the universe is expanding and began from a Big Bang. Yes.
Okay, great.
Okay. Well, how do we know what happened 1 nanosecond after the Big Bang?
That is a lot of speculation. That is something which, if we want to try to say, if for example, the abundances of certain elements and how fusion could have taken place, what we imagine is that when the Big Bang took place, the universe was extremely hot and extremely dense. And if it's expanding outward, you know that when something expands, it must cool. Mm-hmm. And when the universe was very young, you had a lot of what are very high energy light forms called gamma rays. And these gamma rays were very effective at actually dissociating nuclei. But as the universe started to expand, these gamma ray photons, these gamma ray light, gamma ray bundles of energy, as the universe expanded, their wavelengths were stretched out. So all of a sudden, these gamma ray photons became lower energy X-ray photons, and they weren't able to have enough energy to dissociate nuclei anymore. So this was a case which you could actually start to have the conditions of the universe were hot enough and dense enough in the first couple minutes for fusion to take place. There was a high enough temperature, and there wasn't the presence of these photons that would dissociate atoms, so you could have fusion taking place in the first few minutes. But after that, if we imagine how fast the universe is expanding, we imagine that the universe continues to cool off, and these light forms, these light waves, don't have enough energy, and the temperature of the universe becomes too cool for fusion to occur. So nucleosynthesis would take place in the first few minutes of the Big Bang, but then it would cease until the formation of stars, and stars would have fusion taking place in their interiors.
Well, wait a minute now. I thought that we went 300,000 years after the Big Bang, before the universe was cool enough to start fusion, to start forming, well, not fusion, but actually start forming atoms, hydrogen.
Matter.
Yeah,
Matter.
start forming matter. I thought it went 300,000 years before we even started. You said.
Do we know that, though? Do we know
well,
that?
No.
Sure?
Right.
I don't know. Yeah.
And
Go ahead.
yeah. And so you said a few minutes. Is it, so what's the discrepancy?
Sure. In the first few minutes, fusion was taking place, where we could actually have nuclei which were stripped of electrons could participate in fusion reactions. Hydrogen fusing into helium and trace amounts of beryllium. And you're right, when the universe would get older at 300,000 years, up to 300,000 years, there was still a lot of high-energy photons, which, if an atom would form, the nucleus with the protons and the neutrons with an electron in orbit around it, if an atom would form, the photons would have enough energy to dissociate the atoms. The electron will be stripped from the nucleus, so the nucleus would be bared. You would not have atoms, nuclei with electrons around them existing. But after 300,000 years, the universe had expanded so much and had cooled off, and these photons had continued to lose energy. At the 300,000 year mark, the photons no longer had enough energy to dissociate these atoms, to separate the electrons from the nuclei. So now we start to have, after 300,000 years, bound atoms.
Okay. Well, I thought that helium-4, which is the gas that we find here in our natural gas oil wells that is used in balloons and everything. Helium-4 was formed only during the Big Bang, and helium-3 is formed in our sun, and we can find helium-3 on the moon for whatever reason, because it gets blown away from the sun. But am I correct in that helium-4 was only formed in the Big Bang, and helium-3 is found or only formed in the sun?
My understanding is, yes, helium-3 is part of the fusion process. It's actually a very short-lived isotope. And helium-4 is formed in abundance in the sun. And it can actually, of course, we still find helium-4 here on the Earth. Helium-4 is going to be an end product. With stars, when they start to fuse hydrogen, one of the end products which they produce is going to be helium. And that helium can start to gather in the interiors of stars. And, for example, our sun will come to a point when, as it starts to age, it will actually start to burn due to dynamics of the core where fusion takes place, the core will become hotter and will become hot enough for fusion to take place involving helium-4. So some of the helium fusion will take place. The sun will not be able to burn many isotopes of heavier elements, but it would actually, of many heavier elements beyond helium, but more massive stars, like the stars which make up Orion's belt, will be able to fuse heavier elements like oxygen, silicon, and sulfur. We say burning, it's more in the sense that those nuclei are involved in fusion reactions.
Well, and I read somewhere that the sun right now is 23% helium.
Yes.
So it has spent a great deal of its hydrogen supply already.
It's going through that. Part of it was actually when the sun first formed. The sun was not amongst the first generation of stars which actually formed. The sun formed out of a gas which was primarily hydrogen, but had been enriched in abundances of elements like helium, for example, by previous generations of stars, which we think the first stars that formed essentially out of pure hydrogen. And these stars lived and these stars died and then released their heavy elements which they made in their cores through supernova explosions, through other end processes, released these heavy elements into the surrounding space. So the next generation of stars which formed actually had hydrogen with these amounts of the helium. And all the stars that are actually formed now are formed out of the gas which is less, the hydrogen content is reduced, but the heavy element content has increased.
Yeah, otherwise we wouldn't have metals on Earth, right?
Yeah,
and
that's right.
Certainly uranium, which is a very heavy metal. So we have to get, Yeah, it would have to have second or third generation.
Sure.
Yeah.
Yeah.
That was kind of disheartening to me when I found out the sun was not a first generation, but okay, it could be.
Yeah.
Tom, I'm going to get a little bit more theoretical for a minute before we move past this. And I want your opinion, because I know there are a lot of different opinions about this, but we know that the inflationary process, what they call the Big Bang, started 14 billion years ago. If we were to go backwards in time and to basically the instant of the beginning of space-time, I've always wondered about the singularity. If there was we think that there was the singularity that was there and it was infinite, or was there a time when the singularity was not there? The time before that.
And please explain what is a singularity.
Well, sure, yeah.
Sure thing. A singularity comes from, as a mathematical term, like one point of where, say, mathematical equations break down, for example, where the mathematical equations are no longer continuous, and that term has been applied to the Big Bang, and it is also been applied to black holes as well, as a singularity, as one point over here. Where continuity breaks down with the surrounding environment. So the singularity we could think of as a point, an infinite point. We say for some black holes, the black holes don't have a physical surface. We think that there's a radius around them, in which if you go within that radius, your information is lost to the rest of the universe. But we think for the singularity which was the origin of the Big Bang, we could think about it as an infinitely dense, infinitely compact, infinitely hot point. And I know that drives people crazy. Trust me, as a professor, you know. But this is for our thinking of that everything began from this. And it's a very valid question to ask what preceded it. And to a lot of physicists, the questions we simply don't know.
Sure.
And it's some questions, and I'm certainly not trying to be evasive.
I know. I just want to know what you think. Yeah.
I'm comfortable with the Big Bang theory in that I feel like it can explain the observational lines of evidence, Hubble's law. It can also talk about the cosmic microwave background. It can explain these if we apply Occam's razor in the most convenient, way. But there is a lot of things which need to be done with it. It's certainly not there's still things which need to be done to refine it.
It's not the theory of everything.
Yeah.
Have that. Yeah.
Right.
All right. Well,
exactly.
I have a question, and that was I did some calculations on the. We talked about. You mentioned the sun consumes hydrogen. And so I did some calculations, and I figured up, okay, if the sun at a certain rate, if I use that rate over time all the way up to the Big Bang, I find out that 0.1% of the sun's mass would have been converted into energy. And so by doing that, if I multiply that times the universe, then I get a lot of energy. That's 0.1% of the universe, which is, the size of galaxies have disappeared, since the Big Bang. And I see that as, well, how does astrophysicists take into account that much energy has been pumped into a system, thinking of it as thermodynamics here, that much energy has been pumped into the system. Wouldn't that cause the universe to expand? Would that give some of this background radiation that you mentioned about?
You're right in that there has been that conversion. We don't believe that has been enough to actually really drive a lot of the expansion. And you're right to say about the cosmic microwave background to ask a question about what its origin would be. What we can know about it is, when we explain this, we talk about his discovery. It was by some physicists at Bell Labs who were trying to build an antenna. They were trying to make it as quiet as possible. They're looking for all sorts of noise. And one thing they found was in this giant horn, some pigeons had gone in there, nested, and left a whole bunch of calling cards, and these guys had to wash those out. So what we know is that the microwave background is it fills up all space, and it actually is you can best model the emission from it by assuming it's some body which has a temperature of 3 Kelvin. And we can say, okay, what would be something that would produce a temperature of 3 Kelvin? And what we can do is we could say this theory going back to when we think the atoms first formed. Now, you're right about the 300,000 years. And the way you can think about this is up to that moment, light photons were ionizing atoms. And then atoms, when electrons would come back, would recombine with atoms to produce bound atoms, that these electrons would get rid of their excess energy by emitting photons. So there was this balance between photons and atoms interacting with each other. Every atom which, would be ionized, it would lose the electron. There would also be the case of the electron coming back, and electrons coming back, and photons being produced. So you can imagine there's an equilibrium of photons being produced and photons being absorbed. And what would happen at this moment after 300,000 years, all of a sudden the universe was too cool, had expanded so much, these photons no longer had the energy to ionize these atoms. So you can think about these photons are now floating around space. They cannot interact with matter anymore because they simply don't have the right energy to ionize atoms. They're dancers looking for dance partners, and they're trying to expand out in the universe. So if we model how the universe has expanded from 300,000 years ago to today, and we could imagine what was the temperature of the universe at that time, what will be a corresponding energy of photons, and what will be that energy now if we can imagine the universe expanding, and these light waves, these dancers with no dance partners, their wavelengths becoming longer and longer and longer to the point that, what they would be today, we would get photons which are actually about several microns, or microns a millionth of a meter in wavelength. And this is best described as radiation, which is a background sea of radiation with a temperature of 3 Kelvin or 3 degrees above absolute zero. So your statement, when you're asking about if the light from the stars could, and this being energy, could be driving the expansion of the universe and could be part of the cosmic microwave background radiation, while there has been a lot of light produced, I think it still is not enough to really, there's not enough pressure from the light being observed by these to really drive the expansion of the universe as much as from the initial expansion, the inertia from the initial expansion. And we feel like we can explain most correctly that the microwave background radiation comes from this background radiation, because if it was from stars, we would expect there would be an enhanced amount of this radiation along our galaxy. So if you look where the Milky Way is, and you look at a position away from the Milky Way, the Milky Way we can think of as a band, a hazy band, which we kind of see. It's best to be of diffuse light. It's a collective light of many, many stars. And it's best seen on nights, clear moonless nights. And this is the collective light of stars in our own galaxy. From there, the big concern is if this light was actually coming from these stars, we'd expect that there would be this background radiation would have a stronger component along the plane of our galaxy than someplace away from it. And when we look at when we look at this at the microwave radiation, it seems to be very close to being uniform in all directions that we look.
Okay, let me break in there. You mentioned the Milky Way, looking up on a dark night and seeing that, and you mentioned Hubble early on. So before Hubble looked in, was an observer, didn't everybody, all astronomers and physicists think that the universe was the Milky Way galaxy? Nobody.
Exactly. Yes.
And yes. So from that perspective, if God wanted to, he could have stopped right there and not make the rest of the universe. But there's this, we haven't talked about this yet, but a preciseness that, and that was going back to the point, the 1 nanosecond before or after the Big Bang, where it has to be very precise.
As far as the constants,
yeah. As far as the constants are concerned, and we had talked about earlier about a number that was the density of the universe being 1 billion times 1 billion times 500,000 grams per cubic centimeter, plus or minus
0.2%.
Yeah,
0.2.
Yeah. And so that's a very precise, exact number that had to be. If it was bigger than that, it would have crunched. The universe would have already crunched. If it was smaller than that, it would have. We wouldn't see other galaxies. So I just want to get your opinion on that.
Yeah, and I'll just break in. We, as theologians, I was a scientist first, later went back to study theology, but we talk about fine-tuning, and, it appears, it may not be, but it appears to be tuned on a razor's edge to where you've got the strong and weak nuclear forces just as they should be, gravity, all the forces and constants of the that we see in physics to maintain the universe such that life could eventually evolve. It at least has the appearance of being designed or finely tuned. I just want to throw that out to you as an astrophysicist, and how does that hit you, or what do you think about that?
It is very striking. It is very striking that
Okay.
a lot of these constants are just so, and that's been the amazing thing for as we research this. I mean, I think we have an amazing universe to explore and to understand. You may have heard the quote from Einstein: "The most inconceivable about the universe is so much of it is conceivable," and that we could.
Right. Yeah.
And it's amazing that these actually are just so. I ran out of time before in preparation for this phone interview, but there's actually some of the fusion which takes place. Boron is actually an isotope of boron actually has just the right energy level for fusion of heavier elements to occur, because and so boron was a big deal in initial fusion in letting heavier elements form. And as you know, boron is only atomic number 5. It's
Right.
way down the periodic table. And of course, life is carbon and oxygen and phosphorus and all these other heavier elements here. So boron has just the right amount of transitions in its energy levels. I could get you more specifics offline, but
Sure.
but it could actually is also another just so. And I mean, I think it's amazing. I think it's I know there's going to be, of course, scientists who are dispassionate about faith, who would kind of brush this off as just simply coincidence and move on. But it is amazing. It is sobering to think about these constants and these values. Yes.
Well, that's what I wanted to know is that accurate? Because as a theologian, I think that, but I just wanted to know if it indeed is. Now, we could talk about the reasons, whether it's chance or design or whatever, but it is.
Actually, let's back up a second.
Remarkable.
You mentioned, your faith. So we haven't approached that here. We don't know if you're an atheist or if you, or if you go to church.
Agnostic
Yeah.
I am a Roman Catholic, and I'm active in my faith. I found parishes here, and it's a source of comfort. And I actually find that the example of Lemaitre, the Belgian priest, as actually a wonderful example about faith and having a career in science. It is discouraging to me when I'm told by people that how can you have faith? How can you have your faith and still be a scientist? And it's what I do, especially in astronomy. And I don't see a conflict at that. Lemaitre wrote extensively in his life about how he did not perceive a conflict. And certainly he lived the life. I mean, if you look at his scientific accomplishments, and he was doing this while he was studying for seminary, he was accomplished as a physicist. He was, there's famous pictures of him wearing his cassock as he's giving a lecture. If he was not wearing that cassock with his glasses on, standing beside an equation, he would look just like a professor, just like a physics professor. And I think that's something which is very significant there.
I do too. I think that's a picture of faith and science existing in one genius.
And that's what God Talk is all about. Is we have presented, the last show was actually 15 proofs of God. That was, we're scientists and we're presenting these proofs, these arguments that there is God and there has to be, based upon, good, sound scientific judgments, just like so we're using our scientific background to prove or at least present good arguments toward God so that, by all means, we can be scientists.
Right. We want to make the argument for people that you can have faith that's consistent with science. And the reason is so many people today that I meet, especially young people, seem to believe that faith is inconsistent with science. And I don't see that. I don't think that's right. And so that's an interesting example you gave of a picture of faith and science existing in him.
Yes. He, I think it has been frustrating. Carl Sagan was, of course, very prominent and effective popularizer of science, but he, did little to conceal his atheism.
Yeah.
And that, unfortunately, I think makes people think that all scientists are like that, because it's also some scientists, the way science is presented, sometimes people think science is a set of absolute truths and religion is a set of absolute truths. And I think there's also they don't realize about how, science and religion are different parts of the human existence.
Thank you. Yes.
When I want to understand the motion of a particle, I look at a physics book. When I want to understand, when I'm going through trials in my life, I go to the Bible. And these are two things. And I also feel like I agree with you. It has been very frustrating. Kids, very young people today, in particular, see this conflict. And the Catholic Church is a strong, because I know it the best, has a long tradition of Jesuits as, accomplished scientists and mathematicians. The first astronomer
absolutely, yeah,
to actually look at stellar spectra was a Italian priest. And he was the first person to analyze spectra and to come up with a conclusion about about what stars were made of. And to this day, a recent probe to study stellar spectra was named after him. It was a tortured acronym to try to get everything to match up to his name, but it shows a legacy. And I don't know. Many times I get discouraged because I feel like people just will not try to imagine something in between that you can reconcile faith and science. And sometimes I often just throw up my hands, but I don't want to keep doing that, to be honest.
Yeah. And also, you brought up a point there about going to science books and technology and math. When you use that's a tool. And when you're struggling or suffering or going through a difficult time, that's what happened to me. I was an agnostic for most of my life and an atheist, and difficult times I didn't have any tools to deal with that. Strictly with science, and so I came to faith 12 years ago because of that. But I find that they answer different questions, and therefore the problem comes when people do try to read the Bible with a modernist viewpoint, that try to read it like a science book, and we come away with a lot of concrete ideas about the world being 6,000 years old and things like that. A lot of that comes out of the modernistic time frame of the last 150 years. I don't think the pre-modern people thought that way. I was telling Doug that St. Augustine, was 350 A.D., and he was very open to evolutionary ideas at that time, and he believed the universe was much older and things like that. So, I just feel like it's the modern era that we live in that causes these constraints on faith and kind of tries to force God to look a certain way or read the Bible from a certain view. But anyway, that's my soapbox on it.
Yes.
I'm sure you understand.
Right. Well, if we can, go back to our I'm sorry to interrupt you there, but how about a simple question like, what is the ultimate fate of the universe?
Yeah, where are we going?
Yeah.
Where's it going?
Sure. Sure thing. To give a context, assuming a Big Bang origin, assuming an expansion of the universe, you can imagine three possible fates. That you would actually a universe which would expand to a certain maximum size, then mass would actually dominate and and go through gravity and pull everything in, and so the Big Bang would ultimately lead to a maximum size, which would then collapse upon itself. What's called a Big Crunch. That was a late night coming up with that name. So then from there, another idea is for the Big Bang that the universe would start to expand, but would start to slow down, and that in time it would actually be at its at a maximum size. The Big Bang would take place. The universe would expand. It would reach a maximum diameter, and at that maximum diameter, it would actually that would be the end. It would reach an infinite size. It would slow down over time as it reaches maximum. And the third scenario was that the universe would simply expand forever, indefinitely. It would just expand outward. The drawback, what we've actually proven, which is actually we now accept under the theory of, reality is stranger than anything you can actually imagine, is that the universe is expanding, but the rate of expansion is actually accelerating. It's not just the initial inertia from the Big Bang and the universe is expanding, but there's another force which we now call dark energy. And it's something which actually, on top of the expansion of the universe, dark energy is serving to push galaxies farther apart from each other. And this has been a recent development. This was just first proposed in 1995, which, is still very recent by astronomy standards. But, dark energy is a confusing name in its own, because shouldn't it be a force? Because you learned about forces. You learned about forces attracting and repelling. Shouldn't this be some kind of force instead of a dark energy? But
well, let me break in there real quick. You're saying dark energy, and there's also something called dark matter, but they're not really. They're using the word dark to mean unknown. So it's right.
Well, it's dark in the sense that we cannot detect it we cannot use a telescope operating in any wavelength, X-ray, optical, or radio to find it. Dark, that's in, I know it's a confusing terminology. It seems like astronomers have a really bad habit of they find something they can't explain. They have a hand-waving name for something as a filler, but in time that name is embedded in the literature and you have to accept it. The anecdote goes, the Very Large Array in New Mexico, the radio telescope. A Very Large Array doesn't sound like a really impressive name. And when they first proposed it, it was a very large array. And the anecdote I heard was someone thought, well, eventually someone will come up with a better name. And that never took place. 40 years after its commissioning, it's still the Very Large Array. But your question about dark matter, it actually surfaced in the 50s, and first the revelations about were in this early 60s. Astronomers were interested in trying to see what is the distribution of mass in the galaxy. So we think about the Milky Way galaxy. We have this black hole at the center, and everything is orbiting around that black hole. So what you can imagine is, at that black hole, you have this mass, and everything which is in orbit around it, the sun is thought to be about 24,000 light years from the center. If you were to look at the motion of objects, specifically these hydrogen gas clouds, if you looked at their motion as a function of distance from the center, you'd expect that all these velocities would drop. In the same way in our solar system, the 99% of the mass is concentrated at the center. The farther away you get from the center, the velocities of objects slow down. Mercury goes around the sun faster than Venus. Venus goes around the sun faster than the Earth, so on and so forth. The expectation was, as you would get farther away from the center, the velocities of these gas clouds would drop. But the big revelation was these velocities did not drop. They actually came to a plateau and stayed that way. Even for large distances, twice the distance from the Earth to the galactic center, it is still at a plateau, which means that the mass of the galaxy is not concentrated in the center, but it's what's called a dark halo, a giant halo of material around that disk. So every time you see a spiral galaxy, what you're seeing is only a tiny fraction of the total mass of the galaxy. Much more is actually dark matter, which actually encloses all of it. So it was called dark matter because it was manifesting itself through its gravitational interaction through other matter, but it was not being detected not by directly by a radio telescope, by an optical telescope, by an X-ray telescope. It was called dark because it wasn't emitting any kind of detectable radiation. So, so that name became embedded in literature, and we thought, okay, there's much more to the universe than simply matter, baryonic matter, which is protons, neutrons, and electrons. There was also dark matter, which made up this large portion of the universe, and we found there was actually much more dark matter than what there's actually normal matter. And then in 95, discovery was made of dark energy, and we now know there's much more dark energy than there is dark matter. And baryonic matter comprises only 4% of the universe. If you imagine what's called an energy mass budget, equals mc squared, so mass and energy can be converted from each other. If you go from one to the other, you can actually see that this is actually for this here, that there's energy and mass in the universe, this budget, as governed by that equation. Baryonic matter is just a very tiny fraction of it.
And by that, Tom, just for everyone to understand,
sure,
you're talking about matter like protons, neutrons, and electrons, trees, earth, things we see. Yeah.
But also know that, even though it's 4% of the universe, the matter that we see here, Earth, the planets make up a tiny fraction because most of the matter is hydrogen, helium, just floating around in space. Is that right?
That's right, yes. You can think about it because hydrogen is the simplest atom. It's composed of just one proton and one electron. And it actually requires fusion to actually assemble the heavier nuclei. What you need in fusion is actually to bring two nuclei close enough together that they merge together. And that's what goes on inside the sun. So you need high density and you need high temperature. Those are the best conditions to make this happen. So if you have that, you can actually, that's actually how fusion can take place, and that's how all the heavier elements are actually produced in fusion.
Okay. But this dark matter, we don't know what it's made of. I mean, you say it's not made of matter. Right. We don't know what it is. It's dark in that sense.
Yeah.
We don't know what it is. If you can tolerate another quick aside, another line of evidence we have for dark matter is clusters of galaxies. Galaxies are not found as isolated objects as much as they're found in gravitationally bound systems called clusters. And what can happen is, if you look at these galaxy clusters, and you count all the galaxies which are in it, and you estimate how much mass this galaxy cluster has, it doesn't seem like there's enough mass just by visual inspection to actually keep the cluster together. It seems like there's a lot of mass which is missing that will be needed to hold it all together. So that's one evidence that dark matter exists. And we also see, when we point X-ray telescopes at clusters of galaxies, we find that there's this very hot gas which is contained inside these clusters. And the thinking is, well, if it's hot gas, this means that the particles which make up the gas are moving at a very high speed. So this gas should have long since escaped out of this galaxy cluster because there's not enough mass to hold it. All these particles should be moving fast enough that the gravity of just what we see, the mass of just what we see doesn't exert enough gravity to retain everything. But that gas is still there. That gas is still contained inside the clusters. And when we think about that, meaning that there's actually dark matter in this, not only within the galaxies themselves, but also in the space between galaxies and galaxy clusters that can actually attract this gas and keep it in place.
Okay. Well, I have just one or two more questions, and that is, are there any major unknowns in the scientific realm that would point to a divine designer, or is there, anything of that nature?
Okay. For me, I think it's just too many coincidences. I mean, these are things to consider, and of course, to some scientists, it is just so. To them, they would say that it's very interesting that, how the universe could be just at this right critical density. But, I mean, a lot of scientists, as part of their training, separate from their beliefs, whatever those beliefs may be, is to be as objective and to try to what can prove all this. And in these cases, it's possible. It's possible to think about this. I mean, I also for this here, there just seems to be just too many things which are just right. The formation of life to begin with. I mean, if you look at the universe seems to be kind of a very sterile place. Stars form, stars die, galaxies move. And on this little planet, life developed. Life happened, And so if you think of a universe which is extremely efficient, what is life doing here?
Yeah, exactly.
Well, you brought up a good question here, and that is life on Earth. And there was a show that I watched one time is called The Good Moon. That without the moon, Earth would not, life on Earth could not exist because it would, the axis. I don't understand this, but apparently the moon keeps the axis of the Earth very stable, so that we have seasons. If not, we wouldn't have seasons. The Earth would start, the equator would be pointing toward the sun at some times, and then it would just start wobbling. The moon keeps the Earth from wobbling. So I don't understand that, but please. So, that would be, first, please answer that question. And the second one is, could there be life on other parts of the universe or galaxy?
Yes, my understanding is the moon exerted a stabling influence on the Earth to keep it at a certain tilt, to keep it at a certain orientation. The details of that escape me, but yes, the moon has been very favorable for actually development of life here on Earth, and it's something which we can see that. I mean, of course, we know of a grand total of one planet with life on it.
Right.
But we could see, a stabling effect on that. We could think of, for example, if you look at some of the other planets, we know that the planet Uranus is on its side. It doesn't spin like an upright top. It spins on its side. We can imagine that if we find other planets, and we think how planets spin, part of it is dictated by collisions, which occurred when the solar system was very young. And so we think that Venus actually rotates backwards very slowly.
Right.
Venus rotates such that the sun would rise in the west and set in the east if you could see it. Uranus is like a top on its side. And we think, of course, the leading theory for the moon, the origin of the moon was basically a collision with the Earth, which ejected of an impacting body slamming to the Earth. The mantle of the Earth, much of the material was ejected, and the material eventually coalesced to form the moon. We could think about these events. We could think about maybe there was something very fortunate about us having this moon and this body around us, and actually helping to instill life. I mean, Doug has a good point. I have heard about the moon being very important for the stabilizing the Earth's rotation. I want to believe it's something about the effect of the oceans. Would make the Earth slosh around more than it does. But yes, it does play an important role. As for life on the other planets, I believe it does exist. I mean, the caveat has to be, of course, do you mean amoebas or do you mean
complex life,
intelligent life? And I think, there just isn't anything special about our sun as a star, or its location in the galaxy, or the planet Earth as we start to learn more and more about other planets. If you think about just how many stars there are like our sun just in our galaxy, let alone the universe, you just simply by the numbers, you think something, there isn't anything so special about us. Now, just how special we are is a very good question. You may have heard of the Drake equation,
right? Which
is an estimate for this. And the Drake equation, if you in some numbers you put in, things get really pessimistic.
Yeah.
And I'm about just trying to simply communicate between civilizations because the distances are so vast, let alone trying to actually travel from one planet around a star to a planet around another star. So, but I believe, I would just have to believe that there's something we're not all that special. And we might find with the discovery of water on Mars' surface, maybe Mars has a large subterranean ocean. Could there be life there? That's a possibility. You may have heard about Europa, or the moon around Jupiter, Enceladus, the moon around Saturn, which actually has these, look like cracked eggshells. They actually have strong evidence for liquid water. Could life be there too? And even maybe we don't have to look for life in other planets. Maybe it's in our own backyard.
Right. So, is there the probability within the next 100, 250 years that we're going to discover life, communicated life from another planet? Be it, we've sent out radio waves since the very first radio signals. Earth has been sending out radio waves. They are going now, what would that be, 100 light years away, right?
Yes.
So if there is a civilization that's 1,000,000 light years away, but their civilization started 1,000,000 years ago, we would be seeing their radio waves if they start, communicating. So
yes. A friend forwarded to me a wonderful link, and I could send this to you with an image which shows. It shows positions of nearby stars, and it shows an arc showing which TV shows have reached these positions. And for example, the star Arcturus, which is right by the Big Dipper, Little House on the Prairie is just reaching there right now.
Oh my!
Yeah.
Well, this comes from the movie Contact with Jodie Foster,
Yeah.
where they received a portrait of Hitler of some sort, and that's what that the aliens were sending back to us. That was the image that they received, and so they sent it back to us, and it just reached us in whatever year that the movie came out.
Yeah. I'm laughing because I remember that. I remember the characters and how shocked they were that what's broadcast from these aliens is a picture of Hitler.
I guess we kind of glossed over this before we finished, though. I wanted to ask him, with dark matter and dark energy and a black hole, we didn't really define that.
Sure thing.
Infinite density or something? I mean, I've got ideas about it, but I'm sure they're incorrect. So.
Sure thing. Dark matter is thought to be a component of galaxies and galaxy clusters, which we think it manifests itself by gravitational attraction, but does not manifest itself through emitting a detectable radiation. So we're still left to speculate what it is, and a lot of our theories have ruled out that dark matter is composed of anything like protons, neutrons, or electrons. It's thought to be an exact form of matter. Dark energy was detected in the 1990s. It's on a more or less secure footing. It is some kind of force which is actually pushing galaxies apart from each other. More than just simply the expansion of the universe, the dark energy seems to be something else which is pushing galaxies away. We really don't know what that could be.
Okay.
What could be there. Black holes are thought to be made of once upon a time they're made of baryonic matter. They're actually formed. There's actually what are called the stellar mass black holes, and then there are which are only a couple times the mass of the sun, and then there's the supermassive black holes, which are found in the centers of galaxies, and they can be 1,000,000 times the mass of the sun. In the case of the former, we think that they're formed in the deaths of stars. When massive stars die, in the end of the star's life, stars exist by a balance in gravity trying to pull everything in. The energy generating the core by fusion processes trying to push everything out. When massive stars die in supernova explosions, they don't have that source of energy in the core anymore. They just have gravity trying to pull everything in. So gravity pulls all this mass in. And nature has a couple of ways to try to stop this, but it contorts itself a bit. Up to about 1.5 solar masses, there's a limit which electrons and the matter which makes this object up will stop collapse because electrons obey the Pauli exclusion principle, just in case you're missing your chemistry classes. The Pauli exclusion principle tells you that you can only put one electron in per one energy state, and trying to collapse these objects beyond that means putting more electrons in the same state when electrons resist that. If you have more than that, 1.5 solar masses up to 3 solar masses, neutrons actually behave that way. Neutrons behave in a similar way. You cannot pack neutrons more densely than that. But if you have more than 3 solar masses, we don't know of any force which can actually stop the gravitational collapse of this. So this object collapses upon itself forever. And that's what we call a black hole.
Okay.
And we think that the supermassive black holes are the ones which you actually found in certain galaxies, maybe when galaxies were young, first generations of stars formed in the center, black holes formed there. Maybe all these black holes coalesce to form one giant massive black hole.
Very helpful.
All right. Well, now I'm going to show how poor of interviewers we are. I need to now ask you, probably now start the interview and ask you, what is your background?
Before we finish?
Before we finish, I need to,
Sure.
I know we work together and everything, so, you look about the same age I am, but just, please give me a brief background.
Sure. I was born and raised in the suburbs around New York City. I went to college in upstate New York at Rensselaer Polytechnic. I had earned a bachelor's degree in physics with a minor in astrophysics. I did a graduate school at the Department of Physics and Astronomy at the University of New Mexico in Albuquerque. I earned a master's in physics and a PhD there. My dissertation research was on the study of remnants of supernova explosions in nearby galaxies using the Very Large Array. And to this day, my research interests remain on these remnants of supernova explosions, how they accelerate what are called cosmic ray particles, how they produce, they distribute atoms of heavier elements synthesized by stars into surrounding stellar medium. After I finished my PhD, I had 2 postdocs. This is kind of standard for astronomers. The first one was working in Boston. I was at MIT. And then the second one was actually in California. I worked at Caltech. And in 2006, I came to Morehead State, and I've been working here. And I'm now the associate professor of astronomy, of space science and astrophysics. I continue research with students. I also teach. I do the usual, all the hats a professor usually wears.
I'm well aware of those.
Okay.
Have all those hats. You have a great academic pedigree. That's really good. I'm glad we asked him.
Oh, yeah.
Good to have that on there. Yeah, that's something to be proud of. Well, I hope, Tom, before we let you go, we'd like to have you back sometime if you could come back and talk some more physics with us another time. I'd love to have you back.
Absolutely.
Great. We've really enjoyed having you.
Yeah, this has been a great show. I've been fascinated, but I'm a physicist, so
it's been awesome. I appreciate your time, and hope we didn't hold you over and you won't be late. But
no problem, gentlemen.
Okay. All right. We'll see you next time. Thank you, Tom.
Bye-bye.
Bye-bye.
Well, that was a great show with Dr. Tom Pannuti, who really gave us some real inside information about physics and the relationship of the universe to God. And we didn't know his theological background, but he is indeed a believer, a Christian, a Roman Catholic, and that was interesting to find out. But he's a very interesting guy. He's very well versed in his field. I know that, and I know he's got, like I said, the pedigree is amazing. He's been to Caltech and MIT, and he's trained at great places, done postdocs, and has all the credentials. So it was good to get that from the mouth of an astrophysicist.
Well, and that's why we did this. Was when we bring up these topics, we don't want to talk blindly without some intelligence behind.
Well, you're a physicist, but you get somebody who's an astrophysicist. Hear what you got's a preacher, a doctor, and an engineer, a physicist, and NASA scientist, and we do our best to talk about God and science. So I hope everybody's enjoyed the show. It's been a lot of fun. We'll get him back for some more theoretical physics. So this is God Talk, where I hope today we have rightly divided the line between science and faith.
And this is God Talk, while we faithfully examine science and reasonably examine faith. Thank you.
Please visit our website at godtalk.com. Our audio files can be found on iTunes, SoundCloud, and many other podcast platforms. You can find all of our God Talk videos by searching Dr. Andy and Doug on YouTube. Please visit our Facebook page at www.facebook.com/Dr. Andy and Doug. Thank you for listening.